Okay, so let's go throughout how RSA encryption works. So let's start with saying that it's an asymmetric encryption which allows data transmission based of two keys. We have a public key. We use the public key to encrypt the data, and we have the private key. The private key is used for decryption. The security is based on factorial numbers, on the difficult to do a factorial of a large prime numbers. So we see that we will use a large prime numbers, and we will do a multiplication of those numbers, so it will be quite hard to see the factorial of the result. So in RSA encryption, we start by generating a key. We choose two numbers. They are called P and Q. Both are prime numbers and both are large. We compute the multiplication of the two. We call that n. The number n is part of both the public and the private keys, and it is used as a modulus for both encryption and decryption operations. So this will be the modulus. The size of n, usually hundreds of bits, determine the strength of the encryption. So we need two large numbers and two prime numbers p and q for creating of n. Now, totient Euler function, this is given for prime numbers as p minus 1 and q minus 1 for totient function of n. This is a function that tells you how many relatively prime numbers is there in the group between 1 and the number. So totient function of n is like totient function of p times q. Totient function of p times q is like totient function of p times totient function of q. Now for prime numbers, it is the number minus 1. So totient function of p is p minus 1. Totient function of q is q minus 1. There is multiplication between them. So we can say the totient function of n is totient function of p times totient function of q, which is p minus 1 and q minus 1 respectively. Okay? Now the totient function is important because it helps determine the public and private keys. Now choose public exponent e. The value e should be a number that is greater than 1 and less than the totient function that we just calculated of n. So e is a number between 1 and n, must also be co-prime to totient of n, namely the greatest common divisor between the e we choose and the totient function should be 1. Okay, so they don't have any divisor that is common except for 1. Commonly used values for e are 3 or okay, you see, because they make encryption process faster. Okay, calculate the private exponent d. This is the modular multiplicative inverse of e modulo totient of n. In other words, this satisfies the equation. We need now to calculate d, which multiplying by the e that we calculated, this e that is co-prime to totient of n, the multiplication with e gives 1 in modulo of totient of n. This is the d we need. This step ensures that d can be used to decrypt data encrypted with e, because when there will be this multiplication and we will see this multiplication, it will just translate it to 1 and we will see this. So we have the public key, which is n, which is p times q. P is prime, q is prime, both are large prime numbers, and we have the e, this number between 1 and totient of n, which is co-prime with totient of n, which means that this is 1 and totient of n, again, this is this number. This is the public key, and the private key is built from n and d, which satisfy that multiplication of d with e gives you 1 in modulo totient of n, and this will be used for decryption, this d. So let's do the encryption. We'll take a plain message, let's call that m, which is integer between 0 and n. If it's a text, we can translate it to ASCII, for example. and we encrypt the message. How we encrypt the message? We take m, which is a number, and take it to the power of e, which is part of the public key, in modulo n, which we know because it's in the public key. C is the ciphertext. So this is how I create the ciphertext. M to the power of e in modulo n. M is the plaintext message that we want to share. And e is the public exponent from this. Again, e is between 1 and totient of n, and it is co-prime with totient of n. Now decryption. For the decryption, to get m again, what I do is taking c to the power of d. Now, to the power of d means that I take this is c. Think of this one, this part, this is c. Now, think of it, take it to the power of d, what you will get? You will get m to the power of what? To the power of e. Now you take to the power of d, all this in mod n. But we said, remember that we said that e times d, remember here, e times d is 1 modulo totient of n. Now, since e and d are chosen in such a way that the encryption and decryption process effectively undo each other. But I don't remember what says that if totient for totient of n, it's also for n. But we said that d times e mod totient n is 1 and not mod n. The key relationship between the public exponent is totient of n, where e is only totient function and not itself. The reason and not on has to do with the mathematical structure underlying RSA, especially the properties model arithmetic and the way encryption and decryption undo each other. To understand better, let's break it down. Public and private key. This is the key. The decryption process using the private key should be this one. Why E and D are related via the key idea beside RNA that E and D share M. And then this relation holds if and only if the exponents E and D are chosen such that this ensures that applying D and encrypting the message effectively cancel out each other. Y mod n. The reason D is calculated with respect to n is that all the totient function defines the number of integers that are co-prime with n, which is central to how. Since P and Q are relatively prime to each other, the modular inverse of the exist. Since P and Q are relatively prime to each other, the modular inverse of E exists modulo totient of n, which is D, not modulo n. In simple terms, when E and D are chosen to satisfy this equation, the encryption operation align correctly with the modular arithmetic properties. How does this work in practice? Encryption. The encryption, when we encrypt the message, we raise the power of E modulo n to get this. Decryption, when we decrypt the message, raise modulo n. And so for this to recover the original message and the exponent must satisfy this. Why not mod n? If the equation were true instead of modulo n, description wouldn't work as we expected because the properties of modulo n in relation to the modulus and the product with the primes are more complicated and not aligned with our structure. The use of allows to take advantage of number. Why this works? Euler theorem states that if a and n are co-prime, then this is crucial for us, and this examine y equals 1 for any integer m that is co-prime. By choosing the inverse of m, we guarantee the equation ensure that encryption. But y if d times e equals 1 modulo totient n, it means that the e equals 1 mod n. We work on n. To clarify, it's not generally the case that modulo n that n. However, this relationship is not needed for work. Let's break down. The key relationship, the relationship that we know. This means that D is a modular obligation of E modulo n, not n. This guarantees that you raise the exponent to the power n, you recover the index. How modular obligation works? The reason why it works in order function is this. Specifically, it means that 1. This property enables to use as the formation of the chosen n. The key point is RSA allowing the fact that it should end with n, and this is valid when okay, I think that there is something that I just miss. This is valid when e initially this selected so that the exponential process with e and d brings you back to the original set using the structure modulo e. Why not modulo n? The reason we don't require is that e is much smaller. The fact that guarantees that when raising to the power of d is an effective representation. I still don't understand. In RSA, e times d or d times e mod 30th of n equals 1, and in the process we also get that e times d equals 1 modulo n. How can it be? Is the OR function. The equation assures that d is the modular predicate. However, it's pointing out that the relation does not necessarily hold. Let's clarify. Okay. The equation means that if the d is the multiplicative inverse of e modulo, then ensure that for any message, which is the core of RSA, relation would imply so y m to the power of e times d equals m times e times d times 1. It's in mod n, not mod 30th of n. You're correct, and the encryption relies off not mod n. Let's break down why. Other theorem state that for any integer a that is coprime with n, a to the power of 30th equals 1, which is for coprime. Since m the method is typically chosen to be less than m and coprime with n, we have okay. By definition of the RSA key, we have this means that exists some integer k such that when we raise m to the power of ed, we get using the property of exponent, we can write an is this. Since this equals 1, why this equals 1? Since m is typically chosen to be less than n and coprime with n, we have this. Since m to the power of 30th n equals 1, we have this equals 1 and this plus 1, therefore equals 1 times 1. Okay, so the key point is that while ed equals 1 ensure that d is the modular inverse of e with respect to d, the actual decryption process levels error 7. Okay, so we are basing our result on the fact that we take m to be coprime with n such that we can use the property of m times 30th of n equals 1 in mode n. Yes, that's correct. The RSA encryption decryption process rely on the fact that the message m is chosen to be coprime with n, which allows to use the theorem that's derived. In RSA, the message typically integer such that Since n is the product of two distinct prime numbers, most integers in this range will co-prime with n. This is because the only integers not co-prime with n are multipliers of p and q, which are relatively rare. Euler theorem states that if a co-prime, we have this Euler theorem, where b is the Euler totient function of n in the quantified way. This means that for a message m co-prime with n, we can get this. The RSA keys are generated such that we know. This implies that integer we get this. This is the meaning of this. Decryption m to the power of ed, m to the power of k, totient of n plus 1. Applying the properties, we get med, m totient n times k plus 1. This is plus 1, which is this one. So we get from all of this just 1 to the power of k, which is 1 times m. So we get this is 1. So we get this is 1 times k. This is 1. This is 1 times k. So this is just 1 times m. So this is just 1 times m. The RSA is this works because m is chosen to be co-prime, allowing for the ensure that the and if m comes to not be co-prime with m, it may be. How do you know it won't happen? In RSA, it's theoretically possible for the message to not be co-prime with A, but this scenario is carefully managed to ensure that the security and correctness of the encryption decryption process. Here is how it is handled. The modulus n is the product of two large prime numbers. The probability that a randomly chosen message is not co-prime with n is very low. Specifically, m would need to be multiplied by either p and q. Since p and q are large prime, the likelihood of m being multiplied of either is extremely small. Pen is going to further reduce the risk of m not being prime with n, and to enhance security, RSA is typically used with penny schemes such as optimal symmetric encryption padding. Penny scheme transforms plain text message into a format that ensures it is unlikely to be a multiplier of p and q. These schemes also provide additional security benefits, such as resistance to certain types of attacks. Mathematical consideration: if m is not co-prime with n, it means that m shares a common factor with n. This would imply that m is a multiplier of either p or q. In such cases, the decryption process might not recover the original message m correctly, because we need here to rely on that if m co-prime with n, so we get that m to the power of totient Euler of n equals 1 in mod n. This is Euler theorem. This is only if m is co-prime with m. And what do I mean by co-prime? That it only divides with what is the meaning of co-prime numbers? That if I have two numbers, they're relatively prime, their greatest common divisor is 1, namely they only divided both. The only number that only divide both is 1 and not the other one. So 8 and 15 are co-prime because the only number that divides both is 1. And 12 and 80 are not co-prime because their greater common divisor, the biggest number that divide both, is 6. They are also divided by 1, but the greatest number is 6 and is greater than 1, so they are not co-prime, and those are do co-prime. So GCD equals 1 is what we need in order to say that two numbers are co-prime. So let's go back. So we probably say that m is probably co-prime with n, so this will hold. Okay, so let's go back to RSA. Let's go back to RSA. Oh, we where is the RSA? Wait a sec. We were in RSA. Okay, wait. No. Okay, explain on how RSA encryption works. So let's see it again. What? Oh, not ESA. No. Okay. So, Rivest-Shamir-Adleman is a widely encryption algorithm that enables secure data transmission based on the mathematical fact that it's easy to multiply two large prime numbers, P and Q, but very difficult to factor the product. Here is step-by-step explanation of how RSA encryption works. We choose two large prime numbers, P and Q. We calculate the product N, which is P times Q. We calculate the Totti and Euler function, which is P minus 1, Q minus 1. This is because they are prime. And we choose an integer E such that it's between 1 and totient of n, and its GCD, it's coprime with totient of n. Find the modulo multiplication inverse of the modulo. Now we take the inverse of the modulo, and the public key is the pair en, and the private key is the pair dn. Okay, E is this number, n is the multiplication of the prime numbers, d is the inverse of E, and n is again the multiplication of the two numbers. We do encryption. We take the text, which should be a number between 1 and below n, and it will probably be a coprime with n. And then we encrypt the data. We create the ciphertext by taking the m and raising it to the power of e. This is encryption. This is part of the public key. This is not part of the private key. Remember that the public key goes to the public and the private key stays with me. So the sender converts m into an integer using a predefined encoding scheme. Then the sender calculates the ciphertext using public key. This is how it creates the ciphertext. It takes m to the power of the e. This is the number we remember between 1 and the totient, which is coprime with the totient n, which is this one. And this value, this number, has an inverse, which we called d in modulo totient of n. D times E in modulo totient of n is 1. E is in the public key, D is in the private key. In the public key we also have n, which is P times Q, which are the prime numbers, the large prime numbers. The ciphertext, the sender takes the text he wants to cipher, he wants to encrypt, convert it to a number below n. Probably this number will be coprime with totient of n. So what we said is true, namely m to the power of totient of n modulo n is 1. We will count on this as you saw. So the ciphertext, we are taking the text that we converted to a number below n, which is coprime with totient of n, coprime with n, m to the power of e mod n is equal to the ciphertext. Now to decrypt the message, the receiver uses the private key, the d, which is inverse of e in totient of n modulo. He takes this m to the ciphertext to the power of d modulo n, and this recovers. Why it recovers? Again, because c to the power of d is the same as m to the power of, we have e, so e, but with 2 to the power of d, so ed modulo n, and this equals to, now m to the power of, remember that ed can be written as k totient of n, which is, this is the totient, yes, this is the totient of n plus 1, so in modulo n, so this equals m to the power of k totient of n times m to the power of 1, which equals to, now all of this is just m to the power of 1, m to the power of 1, and all of this to the power of k, m to the power of 1, and all of this, because m to the power of 30 and n is 1 to the power of k. Now this m time to the power of 1, which is, oh, this is 1 to the power of k, because m to the power of 30 and n is 1, so this is 1 to the power of k times m to the power of 1, because this one comes from here, and this is 1 times m, which is m. So this was for this place, this, all of this, so we get from here m. As you can see here, we get m. This is, just take this one, take it to the power of d, so it will be m to the power of ed. This m to the power of ed, as I said here, is translated to m, so all what you get from here, which is this one to the power of d, is just m, and we recover the message. Now we can do it in an example. So we have p and q, it should be two prime numbers that are large. Now this example probably didn't do very large numbers, so it will be understandable. So they took p and q, which are prime numbers, and then created n, which n is the multiplication of the two large prime numbers. They should be large. Calculate the totient function of n. Now this is the totient function of p times q, which is the totient of p times totient of q. Now because they are prime numbers, the totient of p, because it is now a prime number, it just asks how many coprime from 1 to this number there are. Now because it's a prime number, there are p minus 1. And again, totient function of this asks how many coprime numbers. Coprime, again, we said two numbers are coprime if the greatest common divisor of the two is 1, namely the only value that divides one and the other number is only 1, not any other bigger number. So the totient Euler function asks how many coprime numbers are between 1 and q. So there are many, q minus 1. So when you're doing the Euler totient function of two numbers, of the multiplication of two numbers, it's like the totient of the 1 times the totient of the 2. So we are doing this, and totient of p is p minus 1 and totient of q is q minus 1, because they are prime numbers. Not every number is just its number minus 1. This is because they are prime numbers, remember. So this is the value we get by doing that. We are choosing a number again between, you remember we have a value for this between 1 and the totient of n, which is a number, we call it e. It's one prime number that is coprime with totient of n, and we don't just draw a number, we find d, which should satisfy that e times d mod totient of n equals 1, namely d is the inverse of e. We use it in the decryption process, so it's important. So d is the inverse of e in modulo totient of n, not n, totient of n. Now the public key is built from e, which is 70 in this example, and n, which is this number in this example. And the private key that only I have, this goes to the world. Someone wants to encrypt, use this to encrypt and then send it to me, and I can decrypt if I have the private key, which includes the d. No one should know the d except the one who decrypts the message, except me. So d is the inverse of e in modulo totient of n, and this is here in the private key, and this is n again. Now we encrypt the message, we take the message, we convert it to a number between 1 and less than n. We calculate the ciphertext, which is the message, to the power of e, which is this number, small number that is coprime with totient of n, which we have an inverse to it, which is called d. So we take the message, take it to the power of e in modulo n. This is the encryption part. The decryption part, we take the ciphertext and then raise it to the power of d. When we do that, it's like m to the power of e times d. Now e times d satisfies that in modulo totient n, it's 1. So we can do that. We can do that. Maybe I want to, maybe we'll show you this in LaTeX. Okay, this is the Euler theorem that for integer a, which is coprime with n, we can say that a to the power of totient of n equals 1 in modulo n. This is what we will use. Now we have those. This is what E and D satisfies. This will be in the public key, this will be in the private key. And we have, this is the ciphertext. We encrypt by taking the message raised to the power of E modulo n. Then we decrypt using C to the power of D modulo n. I wish that it will show you. Now I can say that E times D, oh wait a sec, E times D is like K, because E times D, remember that E times D equals 1 in modulo totient n, so E times D is like K times n, totient of n plus 1, because it's in modulo it equals 1, so it's some multiplication of totient n, which K is some number, doesn't matter, plus 1, because again in modulo it equals 1, so we know that this is what happens. Now when we are doing this, m to the power of totient of n equals 1 modulo n, because we assume that m is coprime with n. This is a fact. When you have m coprime with n, so it means that their GCD is 1, so m to the power of totient n equals 1 in this modulo. Now in the decryption part, we have em, the message, to the power of e, and then this is in encryption. In decryption, we also do to the power of d, so we get e to the power of d. Now instead of ed, I can write this. So I write this. But what it writes here is m to the power of k totient n plus 1. So I can separate it to this. M to the ed is like m to the k totient n plus 1. Now m to the totient n times this one in mode n, as we said, equals 1. So we say that it equals 1. To the power of k, it doesn't matter how k equals, it will just stay 1. And here we have another one, which is here, because it's multiplication, so it's addition of the powers. So we have 1 times m. So in modulo n, what we are left with is just m. And this is how we decrypt the message. This is the decryption part. So this is the decryption we get from this m. So for encryption, we are without the d. We're just doing m to the power of e mode n. This is the encryption. In the decryption, we take it to the power of d, and then here we get the d. So m to the power of ed mode n, and we get m. This is how the RSA works and converts the original message from the ciphertext, and it's based on the difficulty of factoring large number, making it computationally infeasible to determine the private key from the public key. Now let's ask him why we can't determine D from E. Can't we find the inverse, the totient of n, and then calculate the inverse of E, which is D? If we know the totient, you can compute the modular inverse. However, the security of RSA lies in the fact that computing the totient of n is as hard as factoring n. So it's really hard to know the totient of n if you don't know p and q. Namely, you have n, but you won't be able to get the totient of n. You know e, you know n, but you can't get d, because it's hard to get the totient of n without knowing P and Q, and you don't know P and Q. So again, n is built from two prime numbers, P and Q, which are large, and the totient of n is very easy to calculate when you know not n, everyone knows n. But if you know P and Q, which are the two numbers, the two large prime numbers from which n is built, then it's easy to calculate totient of n. But without knowing P and Q, it's very hard to calculate totient of n. And this is the problem why it's hard for the attacker, even though he knows n, he knows e, he has hard time to calculate d, which is in the inverse of e. He has hard time to calculate it because it's hard to factor a number, the number n. Here it is. It lies in the fact that computing n is hard as factoring n. Directly give information about the P and Q. If you can factor n into prime factors, you can easily compute. Conversely, if you know P, you can use it to factor n. This is because it's closely related. Given e and n, you can find it using the external Euclidean algorithm to compute the modular inverse of e. The security of RSA relies on the computation difficulty of factoring large integers. Here is why this is important. Large prime. In practice, P and Q are chosen to be very large prime numbers. Factoring the product of these into prime factor is computationally feasible with current technology for sufficient large n. So, taking a number and factoring a number to its prime number that build it is very difficult for very large numbers. So, no efficient algorithm. There is no known efficient algorithm for factoring large integers. The best known algorithm, like the general number derivative, have a time complexity to make them impractical for large n. Is it hard to factor any large number, or it's hard? No, n is not even a prime number because so it's hard to factor a large number into its prime factors. I think this is the idea. It is hard. Factoring a large number into its prime factors is indeed very hard. This is difficult forms the basis for the security of many crypto systems, including RSA. So it's very hard. I think I think there is something in quantum computer things that is maybe helpful. I think there is something in quantum computing here. There is the Shor algorithm. One notable extension is the potential impact of quantum computers. Shor's algorithm and a quantum algorithm could factor a large number efficiently. However, practical quantum computers offering Shor algorithm of large number do not yet exist. So factoring large number, factoring numbers is always to its prime factors, right? No, it must be right, because otherwise it won't be a factor. Okay, so this is the idea of RSA. It's quite slow, so or maybe we'll see it again for just for a sec. So again, how we work with RSA. We choose two large prime numbers, we calculate n, we calculate totient of this n. We can do that because we know from what n is built. Doing that without knowing P and Q is very hard to find the totient, and here lies the security of RSA. If we can do that very easily to get the totient of n without knowing P and Q, so every attacker would find totient of n and will calculate d, which is the inverse of e, and we'll be able to decrypt the data. Because it is hard to factor large numbers into its factorials, it is hard to find the totient of n because we need the factorials of n to calculate it, and because of this, it is hard to find the inverse of e in modulo totient of n. If we knew totient of n, if the attacker knew it, it will be easier for him to find the inverse, to find d, to find the inverse of e, that we choose an integer between 1 and totient of n, which is coprime, and then we can do d times e modulo equals 1. Now, why do we need that e and v are coprime? I think we need it in order to have an inverse. In RSA, in order for e to have an inverse, if they weren't coprime, e would still have an inverse in mode totient n. I think this is the reason why we need that it will be coprime. Yes, the public exponent e and the totient function n must be coprime for e to have an inverse modulo. This is critical requirement of RSA algorithm to function correctly. This is why we need that they will be coprime in order that it will have an inverse, which is the d, the important d for decryption, in modulo totient of n. So again, we get pq, we get n, we get totient of n, we get e between 1 and totient of n, which is coprime GCD equal 1 between the two, coprime GCD equal 1, and we need this coprime equals 1 in order for e to have an inverse. We calculate the inverse, which will be used for decryption. E times d modulo totient of n should be 1 in order for the decryption to work, as we showed with m. This will be in the power of m in order to create something that will be m to decrypt the message. And we have public key built from e and n, and private key built from d, which is the inverse of e modulo totient of n, and n. Don't be confused between modulo totient of n and modulo n. Sometimes we use this and sometimes we use that. Encryption. We convert the message we want to encrypt to number less than n. We should have that it's coprime with n, but it probably will happen as you saw. Now we encrypt the message. We take the message, e is a number, take it to the power of e, part of the public key that we just chose, and in modulo n. Now for decryption, this ciphertext, we take this ciphertext and take it to the power of d, m to the power of ed, in modulo n, not modulo totient n, modulo n. As we saw with the Euler theorem, will give me that em to the power of ed will be just m, even though we are in mode n, just m. We saw the Euler theorem, remember? This is when a is coprime with n, so a to the power of totient of n equals 1. We used it for the decryption. Because ed equals 1 mod totient n. Now for the decryption, what we do is e times d, because this holds, so e times d k totient n plus 1. So, and we know that m and n are coprime, so m to the power of totient n equals 1 by Euler theorem. Therefore, em to the power of ed, which is this one, m to the power of ed is m to the power of this k totient n plus 1, and remember that m to the power of totient n is 1 because they are coprime in modulo n, and then therefore you get from n to the power of ed m. Just open it up, you get m to the power of 1 times m to the power 1 to the power of k, which is 1, and m to the power of 1 from here, which is m, and you got this. This is the important part. Here we encrypt the message, create the ciphertext, and this is how we decrypt the message. Now, for example, we used numbers and we saw how we got the message again. Thank you very much. This was about RSA and all the rules that are in part of the RSA and how we work with the RSA, and what are the important things, prime numbers, coprime, when it's 1, what we're using, Euler theorem, coprime and the inverse. If you are coprime with the modulo, so you will have an inverse. We use the inverse for decryption, we use the public key, we use the private key. This is the RSA, and how in RSA we create a private key and public key. The public key we give to someone, he encrypts his message, we get it again, and we use it, the private key, which in the private key there is the inverse of E to decrypt the message that someone else did. We gave the public key, someone used this to encrypt, we got the message encrypted, and with the private key, which includes D, which is the inverse of E, we decrypt the message based on the rule you saw. And this is the idea of RSA, and it's based on the fact that we give n, which is the modulo we work with, in a public way. Now the public cannot get the totient of n and cannot calculate from E D to decrypt, because it's very hard to factor a very large number, which should be n. So it's very hard to get the totient of n, so it's very hard to calculate the inverse of D from E, and this is where the security of RSA lies. In quantum computers, Shor algorithm may do a factorialization fast, but now, with the technology now, factorialization of a very large numbers is very hard, so it's very hard to create the totient function, so it's very hard to calculate the inverse of E. So even though we give E to the public, it's very hard for them, because they don't know for what factorials n is built. Even though they have n, they have E, they have a hard time to calculate the inverse of E, which is D for decryption, because they cannot factor n, so they cannot get very easily the totient function of n, so they cannot calculate the inverse of E, because they don't know in which modulo to calculate, because the modulo of E is in the modulo of E that we calculate the D, the inverse, is in modulo of totient n. That's it. This is about some RSA algorithm, this asymmetric algorithm. Thank you very much. If there are any mistakes or correction, please tell me. This is it. Thanks for Mistral and ChatGPT for doing the summarization for me and writing. That's it. Thank you very much.